quantum cultivation, ISES. One of the researchers having exactly half a pick here, half a put here. So he has great understanding of quantum information, quantum science, and quantum optics. So today he is the chairperson, Professor Bimal. Yeah.
Thank you, Prashanto. So it's a great, my friend and long-time collaborator, Professor Sanjay Majumdar, Professor Kharagpur Physics. He obtained his PhD in
Is there any problem?
2001 from India's interests in and related fields. So with this brief, okay, before I invite you, the title of your talk is Quantum Dynamics of Spin Oscillations.
Am I audible?
Can you hear me?
Yeah, I can hear you.
Yes.
I was not able to hear properly Guna's voice actually. So
with this, okay.
Good morning, everyone. Let me thanks Professor Bimalendu Dev, whom I call.
Now you can start.
Okay, thank you, Bimalendu. So let me start by saying good morning to everyone. So I would also like to thank Professor Bimalendu Dev, whom we all call Bimalendu Da, who is actually the person who brought me in this subject, who is like mentor to me. And also I'd like to thank the organizers to give me this opportunity to present this seminar, especially Professor Panigrahi. Okay. So if you let me start it, I don't know, I have to just first share this screen, whether it is available. Are you able to see my screen?
Yes.
I'll make it full.
Make it full screen. Say that.
Yeah. Are you this? Is it okay?
Sure.
Okay. So if you see the title of the talk, okay, so it's saying that spin oscillation dynamics in ion atom. So it's spin exchange between the atoms or ions. Okay, as we know, mostly their dynamics are governed by the magnetic field. Okay, and here what we'll be talking about that something not new. It is phenomenon is known for a long time, but recently got a lot of interest. So if you just can control this spin dynamic using external light, okay. So before I go to the presentation, there is a lot of sort of announcement that if you are interested, some of you, this is targeting to the UG and PhD student who is just beginning in their career. So I am giving a sort of 10 days task crash course on quantum optics. This is from the IIT Tirupati and IISER Tirupati's website. So if you are interested, you can register. So this is starting from the 19th July. Okay. This seminar, what I'm just going to present now, is targeting to the undergraduate students, and also that, as I said, that those PhD students who are just starting, but it will have some kind of flavor for the research also in the advanced level. So maybe I'll not show many equations. I'll try to avoid wherever is possible. I try to explain the concept. And if I get questions, and if you have any doubt, please stop me anywhere. So the presentation's plan is like that. I'll go from the scratch. Like I'll introduce that what is spin, which is a valuable quantum number in quantum mechanics. Okay. So then I'll define some of the parameters. Okay. So let me just take this one. One minute. Sorry. Pointer. So then I'll discuss some of the parameters, okay, which has been used for this quantum technology when you are trapping or cooling this atoms or ions. Those are like a star-shaped, which is many of you know. Then they are being using that some of the nomenclature like magic wavelength, tune-out wavelengths. Okay, this is the corresponding to the light which have been used. Okay. Then I'll briefly demonstrate that in the quantum technology, when the trapped ions are used, okay, so how those ions are used as an elementary level, basically in the how to form the qubits, quantum gates, okay. Then I'll talk about, okay, so what about the phenomena, what actually in the initial phase we'll discuss, that is for the single photon transition phase, okay. If you have that two-photon transition, or two-photon excitation process available, or if you can apply this, what would happen? And there we'll find out a new phenomenon, okay. So we would like to share this recent work, which is submitted in Physical Review A recently. This is the archive reference, okay. So if you're interested, you can look at for the details, okay. So it's talked about the spin oscillations is alta called atomic mix and ionic mixture, okay. And that mixture, okay, when it's prepared and the spin quantum number of this ion atom mixture, how they will be controlled through the light, okay. Certainly magnetic field will be there, but light will have a major role to play the exchange or oscillations, okay. Let me go from the sketch, okay. So as you know that electrons, okay, is one of the fundamental particles. We know its mass, we know its charge very well. But there is some problem that we require an extra degrees of freedom, which is known as spin, to explain some of the experimental fact like sodium D lines, which actually has seen this speed by around 2 microelectron volt. Okay, so to explain that, we had to, means that it was necessary to introduce the spin quantum number. Okay, so there are some quantum numbers, some have to introduce, so that is named as spin. Okay, because it has some analogy. Okay, then I think all of you know that in the Stern-Gala experiment, when the electrons were actually allowed to pass through the gradient of the magnetic field, okay, then in the photographic plate, okay, we are expecting that the incident electron should supposed to show that this kind of classical incidence, picture of the incidence, but what we see that there is a split in the position of the incidence, okay. That split says that the electron should have the spin, which is whose values can be half in terms of the H cross, okay, Planck constant, okay. So what is actually can be found out that the magnetic moment will be, you can express in terms of EH cross by twice MC, which you can write in terms of the spin values, okay. So by knowing this one, so electron has a spin, can you see that there's some changes in the atomic structure? So in the next slide, what you see that due to the spin, what are the changes happened in the atomic structure? So let's take an example of boron atom. So we know that boron, the 2 electrons are occupied in 1s, 2 electrons occupied in 2s, and that is a one bachelor electron, okay, now who is roaming around in a 2p, okay. So if you have this these configurations, okay, then you can think about that inside that atom, you can have that, I think many of you know that spin orbital coupling, which is called LS coupling, Okay, so due to that, these state, okay, get splitted, and we'll get fine structure splittings, and we get a total angular momentum J value is 3/2 and J value is half. So this splitting, okay, is because of this LS coupling, okay, which is inside the atom or ion. Okay. Further, okay, what would happen that the electron momentum can interact with the momentum of the nucleus, and if momentum of the spin of the nuclear is, let's say, half, then that can combine with the angular momentum, total angular momentum of the electron, and give you the quantum number which is known as hyperfine quantum number. And what you see that there is a hyperfine splitting in the energy levels. Okay, so we'll get the half plus 3 half, we can give you the 2, and half minus 3 half will give 1. Okay. Similarly, from the half state, we'll get half plus half equal to 1, and half minus half is 0. So we'll get defined value of hyperfine quantum number, and we'll see that the splitting. Okay. All those things, okay, is intensing in the property. It depends upon how accurately you are looking for the energy level. If you are looking for very fine resolution, so you will be able to see that hyperfine levels, okay. But if you are not bothered about that, you can just go with that multiplies, okay, itself. Now, in presence of the magnetic field, these hyperfine quantum numbers, okay, whose can give you a component, and then we'll get some kind of splitting. So what would happen that, let's say, give an example of the hyperfine quantum number F equal to 0 or 1. Okay, if you had F equal to 1, then it can have that component, magnetic component, okay, which is popularly known. So it will be, let's say, in the direction of the magnetic field. Okay, so that MF equal to -1, 0, +1. So what would happen in absence of magnetic field, these three states, okay, what you see, they are degenerate, means they'll have same energy. But once the magnetic field applied on this, what would happen? They will be splitted. So we'll be able to see them separately. Okay, and these degrees of freedom, okay, can be exploited when you just do the experiment. Okay, now in the experiment, what happened that if you want to do quantum technology, any kind of experiment using these atoms or ions, you need to restrict their motion, otherwise it will be difficult. Okay, so you have to confine these atoms or ions to a certain position and do the experiment. So these three persons, okay, the Stephen Chu, Cohen Tanerjee, and Ben Phillips, they have discovered the mechanisms of quantum mechanisms which can actually confine these atoms or ions, okay, in a particular region, a small span of the space. Okay, so which is known as a laser cooling and trapping. And what they have exploited the Doppler effect. Okay, so if you have that atom or ions, let's say that is having the ground state is 1 and excited state 2. Okay, so you can have the transition from 1 to 2, and which is known as the resonance transition. And if you can shine the light, okay, from the all side X, Y, Z, okay, counter propagating lights, okay, and if you shine it, let's say that lesser than the resonance frequency from 1 to 2, so what would happen that because of the motion of the atoms, okay, it may appear that this wavelength or this frequency with which the light is coming will be able to reach the resonance line. So, but for the photons, for the atoms, okay, what would appear that the frequency of the light, okay, is lesser than the resonance frequency. So it will, or in terms of wavelength, it will be larger in wavelength. So what we'll see that it will say the deadening of the light. Okay, so this is known as actually rate detuning. So in this case of rate detuning, what would happen that people can confine these atoms in the peak position of the pulse or peak position of the beams. So in high intensity region, we will be able to confine the atoms. Okay, why I'm saying all those things, because we will be discussing some of the application, because here we'll see that in the application, this understanding is required. Okay. Now, just one more thing which we require to understand here, that the kind of force, okay, which these lights impart on this atoms or ions, okay, can be calculated, okay. And what one can see that if you have using the counter propagating beams convention, so these force actually proportional to the velocity, negative of the velocity. And so if force goes to the negative of the velocity and there is a proportionality constant, it will be like a damping force. And this proportionality constant alpha can be called as a damping constant. What is seen, what we can see later also, that this damping constant can be understood as a dipole polarity, okay, of the atoms. Okay, this is an internal property of the atoms. So this dipole polarity or damping constant should be significant enough to trap the atom. So the values of this alpha should be significant so that we can trap the atoms. That's a very important quantity. Okay. So how to calculate this alpha, or how to calculate the dipole polarity? So these what would happen when we shine the light to the atom? What would happen? That the energy levels of the atoms are shifted. Let's consider that there is an example of sodium atom. Okay. So here that one about the electron at a 3s level who is actually single valenced. Okay. So if we want to see that what kind of polarization effect this electron got due to the external light with a frequency, let's say light frequency omega, so we can calculate the polarities, which is actually can be written in this format. If you see just carefully, the format has the numerator factor, which is actually is a dipole electric dipole transitions. So if you talk about the V is the orbital, which is at the outside of this outside orbital here, okay. And if you want to calculate that dipole polarity for this V orbital, what would happen that you have to consider that electric dipole transition from this orbital to all the electric dipole possible states. So a summation over n is there. Okay. So this is also known as a reduced dipole matrix element. And what would happen? So En minus Ev is actually depending upon whether n is the first excited state. Okay, this will be the kind of resonance function. Okay, or second one. So depending upon n value. Okay, so what would happen that this will give the energy differences between this this state which you are looking for and the summed over states. Okay. So this is a summation approach which you are taking. And these lights, as I said, this will be a little lesser or little more than the actual resonance transition, because once you shine the light in the actual resonance transition, what would happen that it's like a switching off or switching on. Okay, so you just go to that particular state. So we don't want that one. We want actually to be somewhere close to that proximity so that we can get very good alpha value. That polarity should be very strong. Also, but we will not be going to the particular state. So that kind of wavelength or that kind of frequency we are looking for. And due to that, what would happen that if you shine those kind of light, the energy shift, which is also popularly known as Stark shift, okay, which goes by this half alpha epsilon square. Epsilon square is the intensity of the light. Okay, so as you see that the intensity of light is, let's say, the constant for it will be constant for all the orbitals, okay, or all the states. But what will be changing that alpha value? So when you shine the light, what would happen? Let's say that we are shining the light, so let's say this one, and we have this is our ground state, this is one of the excited state. And if we are having that particular experiment where these levels are involved, okay, and you want to manipulate this transition using the particular light, because of this light, what would happen? The energy gets shifted. Now, if you just plot the polarity, that if you see the polarity profile with respect to the kind of wavelength of the light which you are just supplying, okay, so you will get that the profile is like here. So here that red one is 5D, fast excited state of 3/2 quantum number, total quantum number, and this is the ground state 6s. So wherever these two profile cards, like this is the one, that is the one, and then those are the two positions actually where alpha values of these two, that is polarizability values of the matches. Since both of the orbital get same intensity, so that alpha value matching decides that in these cases, whatever the start shift happened, okay, whether the first state and the second state, they'll be same. So it appears that if you can shine that light, okay, or if you do the experiment using this kind of wavelength like 592, where the polarity gets cancelled, the differential polarity goes to 0, okay, then what would happen that this transition will be like a insensitive to the light. That is a very important phenomena to look at, because the kind of accuracy we are going to look for, okay, they are actually, we should make that this transitions, okay, should be insensitive. Like if you can supply the electron, if you impinge the light which any other wavelength, let's say 350, what would happen that this the line will be shifted by delta 1 and this line will be shifted by delta 2. And you see that since delta 1 and delta 2 may not be same, then there will be some kind of error coming due to the change of the energy level, which is not possible here. So this kind of wavelength where actually we get the matching of the differential, where the matching of the polarity for the two states within which we are looking for the transition, these wavelengths are called magic wavelengths. So they are called magic because they show the miracles, okay, that in that wavelength, the transition, okay, that the transition states are insensitive. Okay, so that's why they are called magic wavelength. Now, what would happen? So if you can shine this, you have to calculate this one, okay, and give it to the experimentalist, and they'll use this wavelength to do their experiment. Okay, that's a theoretician works. Okay, so these are known as magic wavelength. Now, one of the famous example, as you know, that of this optical cooling and trapping, okay, is presently used to maybe in the daily basis. Nowadays available in many places. Okay, is the atomic clock or ionic clock. Okay, where actually nowadays we can get precision at the level of 1 second of, so let's say 10 billion years. Okay, so that kind of we expect the error in the time. Okay, so this is a very good accuracy, but people are trying to get much better accuracy. For that kind of things, okay, where actually atomic clock is used by using that trapping of atoms. Okay, and there that what we have to use, you have to make that transition in such a wavelength so that these two transition frequencies, okay, is insensitive to the whatever light we are using. So you have to use the light to trap. So the trapping light should be such that, okay, that these two energy level doesn't change. Okay, so that is because that these resonance frequencies are used as a standard frequency standard for them. So the most important part is that we have to make the systems, okay, so that it will be isolated from the external electromagnetic field. Okay, so this is one of the examples. Okay, now the kind of systems we will be discussing today is one of the ions, okay, which is known as, let's say, barium plus ions, okay, which is well studied, okay. And it has a variant we are looking for that in the atomic weight 137. Okay, so let me explain in little. So why we are looking for this kind of ion? Okay, because in that, if you want to use ions for your quantum technology or quantum information processing, okay, you should look for something which is scalable. Okay. An ionic system is very much useful for a scalable. Means that if you can make this one of the atom or ions, you can repeat that same phenomena in many of the ions, and you'll get same results. So you can scale it up to extend whatever you like. Okay, and which is important for the quantum information processing or quantum computations. Okay. Second thing is that what you should have, that you should understand this electronic level of this ion or atoms very accurately. Okay, so that whatever that magic wavelength or whatever you are saying that okay parameters you are using will be properly used. Second point in terms of the slide, okay, so you should have very long, okay, very long metastable state, where actually that long lifetime, what I'm saying, so long-lived metastable state. So that we can exploit that presence of the electron in that state. So we will be able to keep that atom in that particular state for a long time and exploit that. Secondly, we should have a long coherence time of the resistor. So what I'll show that we can have the quantum qubit resistors between the hyperfine states of the S and the ground state, okay, S of the state, okay. So as you know that the hyperfine level of the ground state, let's say here what will have that if you have F equal to 1 and F equal to 2, that hyperfine levels will be there. And F equal to 2, though it is excited state, but its lifetime will be almost infinite. So you will have a long coherence will be able to get from this. And here, this first metastable states, it has a lifetime of 30 seconds, which is 3 by 2 is 30 seconds and 5 by 2 is actually 80, almost 80 seconds, which is good enough to the experiment. So here we are looking for the, as you are saying that, looking for the species which has a nuclear spins 3 by 2. So in all this requirement, okay, so what we see that barium plus is one of the ideal candidate and which has been used for a long time, okay, for last at least decades or so, okay. Now, how this system, this ion can be used as a qubit, okay, or qubit resistors, okay. So if you see that you can trap this ion, okay, by optical pumping, okay, which is where actually you are using the counter propagating beam light and take the let me explain this little bit, okay, what is optical pumping. Generally, what happens when you avail these atoms in the from the market, you are getting that atoms in a mixed hyperfine states, okay. And so it can be, some of them are F equal to 1, some of them F equal to 2, okay. So now what would happen for your experiment, okay, where you will have also the magnetic field presence, okay. So all the hyperfine splittings will be available, okay. So you should try to get all the atoms aligned to the particular state. So this optical pumping is a process which actually helps us. So what it does actually, it actually takes the electron for the either F equal to 2 levels to that one of the p states, and using stimulated emission, it can bring, so not this one. So from p state, it will come to the d state by spontaneous emission. From this state to the, again bring it back to the in the ground state by stimulated emission, okay. So these 2 photons, that 1 photon is coming from here, 1 photon is coming for this one, okay. Using that technique, okay, what you can make that, you can make that all the atoms are either in the F equal to 2 state or F equal to 1 state of the ground state, okay. So over time, what you'll see that some of the atoms, so you have n number of atoms are in F equal to 1, m number of atoms are in F equal to 2. So if you want to see the probability of finding the atom in particular states, okay, what you will see that among this F equal to 1 and F equal to 2, what you will see that this kind of a profile, of an oscillating profile. So what we can use, using this idea, using that F equal to 1 and F equal to 2 as a basis, okay, we can make the superposed state, okay, psi, okay, which will be like alpha F2 plus beta F1. But alpha scale and beta scale will say that at particular time, how many atoms are in the F equal to 2 state and how many atoms are in the F equal to 1 state. So using that, what we can form that, you can build up the qubit resistor using the hyperfine states. And that you, as this level, okay, as you see that, as you remember that F equal to 2 though it is the excited level, but it has a long lifetime and it has almost infinite, a very large lifetime. So this will be kind of a coherent registered, okay? This will be, we'll be able to keep it for a long time. Okay. So, sorry. So what would happen that, but what will happen that we can be able to see what is called a Rabi oscillation between these two basis state, okay, and form a qubit. Now, once we form a qubit, which is one of the ingredient for the quantum information processing, next thing, okay, which we'll be targeting is that it is that quantum gate, okay. So using this register, okay. So like I'll give there are a lot of works going on. So I'll give a very naive example of the quantum gate using the trapped ion. So just think about the classical NOT gate, where actually if you have input 0, it will be 1. If you have a 1, it will be 0. So this can be used, this idea can be exploited in the quantum cases by Pauli gate. Okay, where you actually use this kind of a Pauli X matrix, okay, and alpha goes to beta, beta goes to alpha, okay. So what we actually want, if you, by the time you understood that, if you use that qubit to that alpha F2 plus beta and F1, what do you want actually by this NOT gate or Pauli X gate, okay. So you want to shuffle this, you want to flip this state, okay. So this is possible easily if you can just shine the microwave kind of a light, okay. If you shine the microwave kind of a light between these two states or resistor state, okay. So what would happen that the atoms which are at F equal to 1 can go to the F equal to 2, or atoms of which you are F equal to 2 will come to the F equal to 1. So over time, you will be having kind of a flipping of this two. But these also can be achieved using optical light, okay. So that for that you need actually two-photon process, which we'll be using later, and we'll be able to say that what is the advantage of it. One of the advantage, as you understand, that if you can shine that counter-propagating light, which will be actually making the system or experiment better, because you will get a Doppler field case, okay. So the second thing is that getting that laser in optical frequency is easier compared to microwave. Okay, so that is the reason that many people prefers, or many experiment prefers the optical or this kind of Raman transitions using a two-photon. And some people say it's a lambda transitions. Okay, so using that you can get a single qubit quantum gate. Okay, to get that how this coherency is there for this, okay, that depends upon the, those who knows what is the two-photon, which I'll be explaining, okay. So we just don't shine that frequency of the light, okay, to the exact resonant frequency, we'll just shine little lower than that. So that is the detuning frequencies, okay. And from that, there is a stimulated light goes, bring it down to the F equal to 2 level, okay. So it depends upon the coupling strength of this transition from this ground state F equal to 1 to that, say F equal to 2. Or F equal, sorry, not F equal to, this is from the P levels, okay, not P. So it depends upon that ground state, so S to P transition, and from F equal to 1 to the P, and similarly from this F equal to 2 to that P state, okay. So those are G1 and G2. Also, it depends upon how much is that detuning, okay. So that detuning is actually that what a difference in the energy, okay. So if you can shine the lights which is close to the resonance frequency, okay, you will get more coherent, okay. So that's an important parameter for this quantum gate, okay. Now, people would like to make the quantum gate for the many qubits, okay. And that's the advantage because if you can just make it for many qubits, like if you can use or exploit the many atoms together, so you will be having some advantage like quantum parallelisms. And that is possible in the case of the this quantum optics. Okay, that's because that you can make using to counter propagating wave of light, so kind of some kind called an optical lattice. Okay, so if you can have the counter propagating wave, okay, what will happen that you will get a sorry, standing light, okay, standing wave, okay, and either depending upon whether it's a Bluetooth between or if it is a red between, you'll be able to trap that different atoms either in the peak position of the wave or the bottom position of the wave. Okay, so by this process, what you will be able to do, you will be able to trap the many numbers of atoms or ions. Okay. So, and if these are atoms which have two levels, okay, then you will be able to get the if you have having n number of atoms, you will get n qubits, okay, and you will get 2n bases. And you know that, I think you must have heard this process, okay, many times, how the quantum evolution, okay, quantum programming is done, okay. So suppose you want to do this function calculations, okay, using that input I, so which actually you can get in the register, in the second register, okay. So now using this kind of many trapped ion or atoms, okay, what you can do simultaneously, so that is known as quantum parallelisms, okay. So there is the advantage here that using this optical lattice, okay, you will be able to do the quantum calculation much faster way compared to the single qubit, okay. And that you can do it at a glance, at the same run, okay, a single run. Okay. So that's the advantage. Now let's talk about, stop talking about so many qubits. Since we are interested for the quantum gate, okay, let's talk about the 2-qubit gate using that ions chapter. So that is, this is, if you see that this paper by Smith et al. In the PRL, or there are a lot of subsequent paper. Okay, nowadays we can trap ion in the atomic clouds. Okay, if you have a atomic condensate, okay, and bring that ion trap close to that, then what you can do, you can have that electrodes around the systems, okay. So if you want to see that how it works, actually you can either look at this paper, or there's a nice YouTube website is there, okay. So where this is explained very nicely. So what it does actually, by putting the differential charge in these electrodes, so these two will have a negative and these two will have a positive, and which you can flip over times. Okay, what you can do, you can bring that ions inside the cloud, atomic cloud. Okay, so that is the way you can bring them close. Okay, so now if you can make, you can get one ion or two ion, then you can use them as a quantum resistor. Okay, or you can use a quantum gate. So if you consider that one single qubit, okay, so like this example, what you see it here. So like I'm saying that, giving example, barium plus, where actually you have one electron in 6s orbital, so it can have either spin up or spin down. Okay, so this spin up or spin down can be understood like a magnet, okay, bar magnet, okay, and this orientation of the spin can be actually flipped using the microwave lights. Okay, so if you can shine the microwave light, it can be flipped. So this can be used as a quantum bit or qubit, okay. And what we want to see that if you have two of such kind of bits, what would happen? Now here also the phenomena you have to understand that, so what would happen that, you know that in presence of the magnetic field, okay, the up spin and down spin behaves differently. Okay, what would happen that if you increase the magnetic field, up spin, okay, will prefer to go to the higher magnetic field, because in higher magnetic field that will be having the low energy. So this is the plot for the energy versus magnetic field. Okay. Whereas the down magnetic field, what would happen that if you increase the magnetic field, down spin, okay, if you increase the magnetic field, what would happen that your energy increases and system prefers to go to the lower energy state. So it will prefer to go to the lower energy, that is low magnetic field. So if you have, let's say that if you have two of the ions which are at the down spin, okay, what would happen? So this is an example which I'm saying that we are starting with the down spin qubit or down spin atom or ion, okay, and we are putting in the magnetic field. Instead of that, this kind of linear magnetic field, let us put the magnetic field is like that, okay, some kind of bowl shape. So this is the bottom intensity or bottom strength of the magnetic field, and as you go away from this bottom part, your magnetic field increases. Now, if you have a spin down, what would happen? Since as you see that the ions of having a spin down prefer to go lower magnetic field regions, so both the ions would prefer to go to the bottom positions. Okay, but if you so what would happen? You will see that over time they'll come close to each other. But now, if you flip this direction of the magnetic field, what would happen that at this position, the top position, the magnetic field is high, and whereas away from this central position, okay, magnetic field is low. So atoms being down spin, okay, they'll prefer to go away from each other. So if you can flip, what would happen? If you flip the magnetic field, what would happen? That these two atoms will be separated. Now, what you do? You flip the magnetic field, okay, very first, okay, so that these ions will come close again. Once by the time it comes close again, if you flip that magnetic field, they'll go separate. So in that process, what you will see that you will be able to get some kind of motions, okay, between these ions. So what you see here, you can have that attractive and repulsive kind of a force between the ions, okay, and which you can see it, here. Let me see whether I can show you the video. Let me see. Okay, something is wrong. So what you will see that, okay, somehow it is not working here. Okay. Maybe I just minimize it. Okay, yeah. So this kind of the motion you will be able to see. Okay. So now, this is either repulsive or attractive kind of motions. And now what would happen that if I have one of the ion is up, another ion is down, okay, then what you'll see that because that one ion, okay, that which is having that down spin will come in the lower region of the magnetic field, and up spin will go to the higher region of the magnetic field. What will happen that what we will see that the synchronous motion of this, okay, between these ions. So you see the distinct kind of emotional effect between these two. Okay, one is actually kind of a normal motions between the attractive and repulsive motions between the ions. R is you will see that kind of a forced motion, because what will happen that you have flipped the one of the ion to the up spin, okay, by using microwave. Okay, so can we use this emotional phenomena to get the kind of a qubit, two-qubit system like AND. Okay, as you know that AND gates, okay, if you have 0, 0, 0, 0, 1, 1, 0, 1 is 0, 1, 0 is 0, and 1, 1 is 1. So if you can have the down spin 1, 1, let's see that whether we can see that some different phenomena which we will be able to see from the motions of the ions. Okay. So if we can just flip the magnetic field, which is resonant to the attractive and repulsive forces, okay, so then what would happen that you will get a very faster resonance kind of faster oscillations of this one compared to the oscillation what you see it here. So okay, so you can distinguish these two oscillation mode, okay, by one is faster, one is slower. So if we can make a kind of a setup where, sorry, what is happening? What is that? Okay, I think I lost you. You can set up a setup where actually you can allow this two ions, okay, to move to move in the magnetic field, where the magnetic field is flipping, okay, is resonant to that the attractive and repulsive force, okay. Then you will get that when both the ions are down spin, you will get faster motion, and when they are in opposite spin, they will be slower motion. So we will see that the effect only when they will be in a similar spin, and when they are opposite spin, there will not be any effect. So when I pass the system to that kind of magnetic field, we will get a resistor. So and kind of gate will get. Okay. So basically, this is one of the technique, okay, which has been used by experimentalists. And as a summary, what we would like to show that in these cases, what you see that two-qubit logic gate can be obtained, and the basic phenomena is that you will get the spin oscillation to be exploited. So that is the basic thing. So using this spin oscillation, okay, you can manipulate or you can construct many of the gates or many other circuits. Okay, so this idea can be exploited in our subsequent presentations. Okay, so spin oscillations. Okay, now here what I'm going to talk about, that this spin oscillation cannot be controlled, unlike that magnetic field using the light. Okay. So here again the candidate is that like barium, single ionized barium, and where the clock transitions is from the D to A states. Okay. So and I said that this ion is very good for the quantum technology because of all the phenomena which we have discussed so far. Now also we said that the dipole force, okay, which is required to control, or which is required to trap these systems, okay, the ions, and that goes by that the dipole polarity, okay, which is the damping force, okay, the damping constant, okay, and that should be significant enough. And what we understood that we should shine that light, okay, at the magic wavelength, okay, so that the whatever happened, okay, whatever happened, it should not disturb the energy level of the ion atoms. So one more thing which is very important here is that where the dipole polarity goes to zero. Okay, so if you see that the energy change due to the external light which is used for trapping, okay, if you can make such that particular energy level is not shifting. What does it mean? Means that polarity values goes to zero. Okay, that will be some of the experiment. It will be very ideal. Okay, like that quantum resistor what we talked about. Okay, or qubit whatever, where we are just looking for the ground state only. So if you can just make sure that ground state is not perturbed by the external light, we are just we are very happy. Okay. So this kind of wavelength at which, okay, we don't see that any change in energy level of particular state due to the external light is known as tune-out wavelength, okay, or magic. Some people say magic zero wavelength. Okay, so now this can be easily evaluated from the calculation. Experimentally, it's not possible to find out, but from the theoretical calculation, what you can find if you use some linearly polarized light, okay, and if you look for the polarity versus wavelength or the particular state, okay, which we are looking for, like a ground state of the beryllium plus ion, we'll see that at some position, at some wavelength, okay, the polarity goes to zero, and that will be the tune-out wavelength for the particular state or the particular ion. So at this tune-out wavelength, so if we are assuming that f equal to 1, what would happen that your particular state will be insensitive to the external field, electric field, but the excited state will see that shift. While in magic wavelength, both the states will be shifted, okay, but the difference between the energy level difference between these two will be unchanged. So that's why, so depending upon the experimental requirement, you choose what kind of wavelength you want to use it. Now let us consider in the tuned out wavelength. Here we are used to linearly polarized light, okay, but if you use circularly polarized light, what would happen? Now if you look at that expression of the dipole polarity, it has three terms. One is the scalar terms, the tensor terms, rank 2 tensor, and there is terms which is known as vector terms, which depends upon the sigma. Sigma is a spin of the light. That means that it signifies, or it actually tells about the polarization. So if you have a linear polarized light, sigma is 0. If you have a left circular polarized light, if sigma is +1. If you have a right circular polarized, sigma is -1. So depending upon the kind of the light we are polarization of the light which we are shining to trap, okay. So whether we'll get the contribution from this term or not, it will be decided. So this term whether it will be 0 or non-zero. Okay. So this term will signifies, okay, that okay it will just addition. It will like additional effect, okay, compared to the linear plus light. Okay. Also, it depends upon the which quantum state, okay, energy level state we are looking at. So if you are looking at mj equal to 0 level, that is magnetic quantum number of total of j, okay, that is 0, okay, then this will not contribute, okay. So if you look at it, okay, in terms of the contribution, okay. So if you have a circular polarized light, you will get non-zero contributions. And also this term highly depends on the non-zero values of the mj. Or if you want to convert it in terms of hyperfine level, okay, so you will have to multiply the factor and get the corrections, okay. And so what you will have that you will have a MF level, okay. So for particular MF level, if it is non-zero or 0, okay, so this term will contribute, okay. So if this MF is 0, then what will happen? This term will not contribute. So what we'll see that if when you look at the profile of the polarity with respect to the wavelength, okay, the black line showing that when MF equal to 0. And this is causing that 0 polarity at this particular wavelength, okay. Whereas what we'll see that there will be changes because if we are signing that the circular polarized light, okay. So then what would happen that MF equal to -1 and +1, they will be modified according to these extra terms, okay. So what will happen that there will be shift, okay, in the tune out wavelengths for MF equal to +1 and -1, okay. So we'll have that different tune out wavelength for this different magnetic quantum number of the ground state, particular F equal to 1 state, okay. So now, so if I just say that what is the wavelength where actually MF equal to 0 goes to 0 polarity, at that actually you can find it 480 nanometer around this. Okay. Now let us see that one nice effect of this. Now if I just zoom this part, what would happen that at this wavelength where MF state goes to 0, that MF polarity of the MF state goes to 0, but the other states, MF equal to +1 or -1, will have a non-zero polarity. That means it will have a non-zero energy, because as we understand that polarity multiplied with the intensity of light will give the energy shift. Okay, so at this wavelength where polarity of the MF goes to 0, or tune out wavelength of the MF equal to 0, what would happen? This MF equal to +1 and -1, okay, sorry, -1 and +1, they will be having non-zero energy contributions, which appears like that, okay, if you have a external magnetic field, okay, what would happen? You will get similar kind of phenomena. Okay, so you will not get any contribution from MF equal to 0, but you will have a shift or splitting of the MF equal to +1 or -1 energy level. So what we can see that this splitting, okay, at that tune out wavelength, okay, of F equal to 1 state, okay, this splitting can have an analogy with the external magnetic field. So this, by the time, this we are getting from the light. Okay, so this is from the polarizability calculations we got it. So this is getting from the light. So this splitting, okay, which we got it from the light, okay, can have an analogy with the external magnetic field. Okay, so that's why, okay, we'll see that some people say that it's called fictitious magnetic field or synthetic magnetic field, okay, due to the external light, which is having a polarization of circular polarizations. Okay, so this is significant. As you see that in atomic unit, this is that, and if you multiply it with the intensity, you'll get energies. Okay, and then you can convert. So from the shift, you can convert how much Gauss it is. So then you can compare the external magnetic field and this magnetic field induced by the external light. Okay. So now the next few slides, what I'll see that so that whether we can exploit this external synthetic magnetic field or fictitious magnetic field, okay, to do the spin exchange mechanism. Okay. So before going to that, there is one more phenomenon which I want to introduce. That so far we have talked about the single photon transitions which are being used, but as you know that for over a long time it is known that that two-photon transition can give many other cases much better. As I said in earlier also, okay, two-photon transition can be available in the optical range. Also, it will be the Doppler-free kind of a system. Okay, so that has the advantage for two-photon, especially when actually earlier in age, one has to excite that atom to the Rydberg state, and we didn't have a laser to excite. Okay, we didn't have a laser to excite that at that wavelength. Okay, or at that high energy region. Okay, we had to use the two-photon to excite that, two optical photon or two optical lasers. Okay. And there have been a recent use of this technique in the atomic clock. Okay, so two-photon, which makes the better accuracy or gives the better accuracies. Okay, so in our cases, okay, we would like to use this two-photon for the barium plus. Okay, and where we use that two-photon, one is photon actually is pumping that electron from 6s to the any allowed excited state, and another photon is bringing it out to the 5D levels. Okay, so if you want to calculate the starship of these two states, okay, we can calculate easily using this expression where you have to use the dipole polarizability for individual photon, and that is one is with the omega 1 and omega 2. In this case, there is one restriction is there. Restriction is that the difference between these two frequencies should be that difference between these two energy levels, okay, between 5D and 6s. So that is a restriction. That means that if you know this one very accurately, okay, and so what would happen if you know the magic wavelength for this system, okay, where this correction goes to the separation between this differential correction of the energy goes to 0, then what would happen that knowing omega 1 will be able to fix that omega 2. So one of the wavelength actually is sufficient to evaluate to get the other wavelength. Now here, what would happen that we have used both the light having the same intensity, and so that this term, the factor becomes 1, and we can have the effective dipole polarity is alpha 1 plus alpha 2. Okay, don't go to the details. But we want to talk about what is the consequence of this. Now, if I look at compared to the single photon magic wavelength, where we are just looking for where polarities matches between these two states, here if you say the two-photon cases, compared to here, you get many more magic wavelengths and many more points where actually these polarities matches. Okay, that means that we'll get many more magic wavelengths, which will be useful for experimental purpose. Our interest is not magical, our interest is tune-out wavelength. As we see that when we had a single photon, we have only one single tune-out wavelength. But in the case of two photon, just like a magic wavelength, we'll get extra tune-out wavelength. Okay, so this is you see that we'll get that omega 1 equal to 533 and this omega 1 equal to 632. Correspondingly, omega 2 can be evaluated using that constraint which we have talked about. So now, if we see that, so this is using the linearly polarized light. Okay. Now, so what we got it? We got a 2 tune-out wavelength. Now, if we just having that now circularly polarized light, what would happen? As we explained, that there will be shift in tune-out wavelength for the MF equal to +1 or M equal to -1. Interestingly, that at these two tune-out wavelengths, two set of tune-out wavelengths, what would happen? That there is something interesting happening. If you, this is very difficult to see that, so I just zoomed it, and you see that here that MF equal to -1 having the positive value at the tune-out wavelength of MF equal to 0. And MF equal to +1 is negative value. That means that here the contribution shift to the MF equal to +1 is negative, whereas means energy pushed will be negative, and where MF equal to -1 is pushed to the positive side. But what you see, it is opposite at the other tune-out wavelength. Okay, so here that MF equal to +1 goes to the positive side, MF equal to -1. So what would happen, the kind of fictitious magnetic field what we are talking about, okay, at this tune-out wavelength, it can be positive, then here it will be negative. That's the interesting phenomena which actually have to be exploited. Okay, so this is the one interesting phenomena which we observed, okay, in these cases. Okay, so we get different sign of the magnetic field, okay, at different tune-out wavelength. Now, let's exploit that phenomena in the case of one of the application which wants to that ion atom scenario. So as you know that we can bring that ion close to the one atomic cloud of condensate, okay, and as we have explained earlier that using that electrode we can bring it close and get a pair, okay, and a mixture of this. So if you can just think about the one atom and one ion, okay, ion we are talking about barium plus and atom is rubidium with this atomic weight, okay. And if you are looking at the ground state F equal to 1 and F equal to both of F1 equal to 1 for the barium plus, so F1 equal to F2 means the F value is 1 for the rubidium also. So what would happen that if you have applied magnetic field or not, the magnetic quantum number of these two mixtures. So this one, barium plus I'm just putting as a red and rubidium I'm putting as blue. What would happen? They will have a, these are the possibilities. Keeping that total magnetic quantum number is constant 0. Okay. So if you consider 0, 0, +1, -1, -1, +1, and both the cases total magnetic quantum is 0, and these will, okay, will have, okay, will be almost same energy if we don't apply any external field, because okay, they are in the ground state, okay, and they actually do not get splitted due to the magnetic field. Now, what would happen that here we apply now magnetic field also, okay. So we expect this kind of degeneracy will break, okay, whatever is there. So, and along with that, what would do that we'll shine the light only to the ion, barium plus. By making such that we just choose the tune-out wavelength of barium plus, okay, which is far away from the resonance line of the rubidium, okay. So this light will not affect the atom at all. So what we will see that we will see the changes of only this one, okay. So using that light, we want to see that how we can manipulate. So what we will see that we will have a stark shift of this ion, and using that stark shift, we can play some interesting phenomena. So we just make the magnetic field variable, we increase this. Okay. So let's start with the when there's no field. Okay, when there's no field, what would happen? The 0, 0, +1, -1, and -1, +1. This spin or this hyperfine quantum number, okay, will have same energy. So they will be designed. Okay, but there is no magnetic field. Okay, so but they will not be able to exchange one state to another, or we will not be able to oscillate or not oscillate, even if exchange is not possible. Okay. Now, our idea is to explore whether can we have the oscillation between this using the light and changing the magnetic field. Okay. So now let's see that when there's no light, no magnetic field, since they are in a degenerate state, we'll be able to write there in a superposed state. Okay. So these are the coefficient, square of the coefficient tell that how many pairs are actually in the 0, 0 state, how many pairs are +1, -1, how many pairs are -1, +1 state. Okay. But because there's no magnetic field presence, we'll not be having the oscillation or transfer from one state to another state. Now, if we apply the magnetic field, what would happen that this degeneracy breaks up. So what we'll see that this pair will go up and this pair will go down in the energy level. And being the 0, 0 MF value, okay, so this will be unaltered, this energy. Now, if I just look at that energy difference, okay, between from this 0, 0 level to the +1, -1, -1, +1, we can calculate using Bright-Rabi formula, where actually you have that term which is Hyperfine splitting term, okay, and this term is the same for all the three states, Okay. So when if you take the difference, this term will be cancelled, okay, and what you will get the contribution only from the magnetic field dependent terms, okay. Now, if you see that, so there will be shift, okay, in this energy level of delta E plus and E minus because of the magnetic field presence. And if you just calculate, what you see that, so here because of that, this one, presence of magnetic field, we will be able to transform from this state to, depending upon magnetic field, from 0, 0 to +1 or -1, 0, 0 to +1, -1, +1, but there will not be any oscillation because they are not degenerate. So to have the oscillation, we have to bring them to the same energy level, okay. But fortunately, at a particular magnetic field, okay, that +1, -1 state comes back to the 0, 0 level, okay. And then what would happen? We get the degeneracy between these two levels, 0, 0 and +1 or -1. And because of the presence of the magnetic field, now we will be able to get oscillation between these two. And that happens in 5.45 Gauss. Similarly, okay, so we'll get a spin oscillation between these two. But this oscillation that between this 0, 0 to -1, +1, since that energy, okay, is constantly going down, there's no possibility to become dissonant, okay, among these two, okay. So we will not have any spin oscillation between these two, okay. So 0, 0 to -1, +1. But if we now apply single photon light, or if we allow the single photon transition light at the tuned-out wavelength of 480 degree, what we said, we'll get additional changes because of the fictitious magnetic field. And as I said that, okay, this will have an opposite sign, and what we'll see that even at 0 magnetic field, okay, we'll see that split because of this fictitious magnetic field contribution. So this splitting is purely coming from the light, okay. And as we increase the magnetic field, what you see that these state energy separations, okay, they are constantly going down. But after a larger magnetic field, there is a crossing of this, or so this energy difference becomes 0 at some 12.40 Gauss. Okay. So at that higher magnetic field, what would happen in presence of the polarized, circularly polarized light, okay, what we see that spin oscillation is possible between 0, 0 and +1 or -1. But still 0, 0, -1, +1 is not possible, okay. But if we have that two photon transitions, okay, what would happen then? As you see that if you choose the different tune-out wavelength, and as you see that at different tune-out wavelength, the sign of the magnetic field changes, and instead of having +1 and -1 here, this will be converted to the plus because the magnetic field sign is changed. Okay. So what would happen? This will boost the energy level. What was 0, that will be boosted up to making a positive. okay, at geomagnetic field. And what we'll see that there is a possibility if you shine the light at particular 532 tune out wavelength, there's a possibility to have some particular magnetic field values, okay, the 9.95 Gauss, okay. So you can have the 0, 0 and -1, +1 spin, okay, state, mixture state, they will be degenerate. And at that particular magnetic field, you will get spin oscillation between these two. Whereas still you will get that a spin oscillation between the 0, 0 and +1, -1, but at higher magnetic field. Okay. So this is the advantage of two-photon cases, that what will happen that we get both the oscillation, make it possible just by tuning the wavelength of the light. Okay. So by tuning the wavelength of the light at two different tune out wavelength, we can make both the spin oscillation possible. As a nutshell, okay, what we saw it that at geomagnetic field, what we saw that all the states, all the mixture spin states are degenerate, but when there is a magnetic field, okay, but with or without presence of the light. So if it is present, but if it is a milliamperes light, okay, so we'll have a spin oscillation between this 0, 0 and +1, -1 at 545 Gauss magnetic field. And we get at higher magnetic field, okay, if you have a circular plus light, we get the same kind of spin oscillation. But to get both the kind of a spin oscillation from 0, 0 to +1, -1, -1, +1, +1, -1, we need two-photon cases to use it. So in summary, let's conclude it. Okay, so what we actually try to explain you in the very briefly that we demonstrate that how qubits and quantum gates can be manufactured using the spin degrees of freedom of the ions. Okay, and what also we discussed that how is spin exchange possible, or spin oscillation can be controlled, okay, using external light as well as magnetic field. It is known that using magnetic field, okay, for a long time it is known that using magnetic field it can be done, but using also external light, it can be possible. That is the things which we have shown in this paper, okay. So, Argo is submitting this thesis. Onol and Norden, who were there earlier in our group, so they are actually co-author of this paper, which is submitted here. And if you are interested, please look at this paper. And I would like to conclude by thanking you all for your kind attention. And I would like to have some question and answers if you can just raise it. Thank you. Thank you, Anthony.
Now we are open for questions. Are there any in chat box?
No, sir. There are no questions in the chat box.
Okay, so queries can be asked directly. Please unmute yourself. So I have a question.
Yes.
You know, this ion qubit, which sort of is being marketed, you know, this 20 qubit one.
Right.
So what is the, what kind of, the principle what you are telling, is it the same principle which works there? I mean, what is the...
No, this is one of the naive one which actually I explained, because for the explanation it is very easy. Okay, so, but in principle actually where those many qubits are there, okay, so 20 qubits or so they use different technologies, okay. So it is a little complicated compared to what we explained. Here actually is a very, very elementary way I explained, okay, so that it can be understood, okay. So maybe I should give you that some kind of references where those are used, okay. Some recent work have been done on those.
And this other thing may not be completely related, but, this angular momentum transfer from, spin and orbital, those kind of things.
Right.
So, see, for example, there are this Korn's theorem, which allows the center of mass to decouple. Similarly, orbital angular momentum and spin, are there any other kind of thing? Because orbital angular momentum will be related with, this, basically just like center of mass, it will be like the difference in coordinate. Are there any theorems there with regard to?
I don't have a knowledge about that. So I'm not able to answer that. Whether there's specific theorems which can actually apply there. So I'll look at it.
Okay. And what are the places, for example, where you have a good collaboration with experimental people?
Yeah, that's what we are trying to work with the Mainz, the University of Mainz group. Okay, so they do experiment on ions. Okay, that there's a Ferdinand Schroeder. So who actually they have done a lot of. So still they are working. Okay, a lot of things on it. Okay, so they have, and also that Rainer Blatt group in Innsbruck. They are doing also using the ions to build up the quantum computer. Chris Monroe group in the Maryland also, they are also using it. So there are many groups are using this.
I think there's a question now in the chat box.
Yeah, there is one. So it is there any other atom other than barium which can be used as qubit register? Yeah,
there are, as I said that, there can be many of them if those criteria which I actually categorize, okay, that is satisfied. Like ytterbium plus, okay, strontium plus, okay, those are very popular ions, okay, which are being used, okay, to construct this kind of qubit or register, okay. So there are many of them out there. Even calcium plus, people have used calcium plus.
Now, since this ion motion is slow and electronic degrees of freedom are fast, do you take advantage of like this Berry phase kind of thing? For example, here
actually, that is the next phase of, that is you can use the Berry phase in there. So I didn't talk about those things.
Okay.
So you can use even if you use that different kind of a beam, like the vortex kind of beams, okay, there also you can see that signature of this, okay, where actually there's a azimuthal variations, okay, azimuthal symmetry is there.
Okay, so if there are no more questions, let us thank Sanjay for a very nice talk.
Thank you for your kind attention and giving me such a good opportunity.
Thank you, Sanjay.
So I'm just logging out.
Yeah, sure. Akhil, if you are around, we can have a few more minutes.
Yeah, you are asking someone?
Yeah, you take your time, because you have finished little early, no problem. I was just checking with Akhil if he's around.
Okay.
Yes, I'm here.
Oh, good. So Akhil, you can, if it's okay with you, we can start. I can introduce you. We can start, no problem. Huh?
Yeah, I can start.
So it's a pleasure to introduce Akhil Pratap Singh. Akhil spent one summer here, and that is the summer where I had a bit of a problem with my eye. But amazingly, Akhil, more or less on his own, with telephone calls from exchanges with me, finished a very nice paper on nonlinear science. That probably hooked him to science, and then we went on to do his PhD in Japan in a very prestigious place. Professor Nakamura is going to give the talk. We are going to hear. He's sort of at a place where, like this real big quote-unquote quantum computers are being produced right now at the laboratory stage, but eventually it will become technology. Maybe already there are some technology coming out of it. So, and as Professor Bhanu has pointed out, quite a few of these things what you are talking about will be checked in this platform, which is led by Professor Nakamura. And so we are going to get really a bird's eye view of what is happening from a happening place. And I think that was the first group which the superconducting flux, right? Flux tests were used, right? Flux qubit.
Yes. Box, yes.
Yes. So Akhil, you can now talk, although you had half an hour, now you have 10-15 more minutes. If you have more, you can go ahead because there is a bit of gap there. So you can take a little more after your time if you have enough material, not a problem.
Okay, so let me share the screen. Then I can just let me know if you can see. So is my slide visible?
Yes, it is visible. Yeah, perfect. Yeah.
Okay, so thank you so much, Professor Panigrahi, for kind words and introduction. I'm Akhil Pratap Singh. I'm a graduate student in the Nakamura Osami Group in the University of Tokyo. And first, I'll like to thank Professor Panigrahi and whole of the organizing team for QIQT21 for giving me an excellent opportunity to speak here. I have participated in a few talks and it has been very interesting summer school so far. Today, I'll be talking about an overview of superconducting qubits because this is what I have been associated with. And today I'll try to speak more from an experimentalist point of view rather than going much into mathematics and theory. So it's about 30 minutes talk and please feel free to interrupt and ask questions at any point. And I'll try to be very introductory about this topic because I know the audience is from various fields and very wide physical like fields. So I'll just try to give a gist of superconducting qubits to everyone. So let's start with the topic of this summer school itself. So we all know it is quantum information and quantum technology, but let's just first focus on three words: information and technology. So we all know very well about information and technology, and especially in India, because this is huge industry. And according to a NASSCOM report, it contributed about 7.7% of India's GDP in 2017. And this field is just growing exponentially, and there is no looking back for this field as of now. But what makes this summer school and this topic in general very special is when we merge this with quantum. So as we all know, quantum brings very distinct features, which some of them we don't see any classical analog to it. So just to show that there is quantum physics special features like interference, superposition, and entanglement. So what we tend to achieve is to combine this quantum with information and technology and to make quantum computers and quantum information and technology more robust, secure, and fast as compared to their classical counterparts. So to make quantum computers, we have to make a bit or qubit. So qubit are nothing but classical bit, which we see 0 or 1 in classical computers. And to realize those, we have whole different set of candidates in physics to achieve those experimental qubits. So this is not an exhaustive list, but it considers very prominent and important experimental candidates to make qubits. So they all have their own work, research, and they have been like developed very fast and explored quite a lot. But one of the candidate in this stands out in terms of its promise to deliver and to fabricate it, and that is superconducting qubits. So in this talk, I'll talk about superconducting qubits. It is not possible to tell a lot of things about superconducting qubits just to give an intro about it. So the agenda would be to talk and tell about superconducting qubits, to get familiar with it, and then to tell how do we control and measure it. So in the first part, I'll focus on 3 subsections: is what is superconducting qubit, how it really looks in reality, and a small mathematical model. And then we'll talk about how can we access them. So let's start with the very basic fundamental experiment of physics, where we see the spectrum of light. So if you pass a light through a prism, we see emission spectrum, and we see discrete wavelength and discrete color of light. And this color has a discrete pattern associated with each atom or molecule, and these have very distinct spacing between them, and color and wavelength. So here on the right side, you can see you have energy spacing, and this is for particular pattern. You have energy level. You can give a proper energy with respect to the spacing between any 2 energy level, and the atom will excite to that state, and then when it emits the specific amount of energy, it comes down to ground state or any lower state. So this has, we can see this is not a continuous spectrum, but rather it is discrete energy level spectrum. So why I'm talking about it is because we want to utilize this atomic structure to qubit space, because as we know, qubit means you have 2-level system. So what we want to extract from this atomic structure is to get 2-level, and that could be our qubit. So which can also be intuitively illustrated by block sphere. So if we make qubits from natural atoms, then it has enharmonic degrees of freedom. It can be very well isolated from environment and thermal bath. The losses would be very low. And the level diagram here, the energy level diagram, allows for qubit-specific control and readout. So depending on which level we want to, laser pointer. Okay, so which level we want to access, depending on that, we can just do control and readout. And of course, there are always higher levels. So it is not possible to get rid of them, but it is always possible to only access any 2 levels. And mostly we just access most lower, like ground state and first excited state levels, which we call 0 and 1. And that makes up our qubit. So are these really qubits? Like I just said, they always have more degrees of freedom, and they are always approximate 2-level system, because there are always higher levels which tend to play when you do some experiments, and they have certain effects on them. So what is superconducting qubit? It is nothing but an artificial atom. So left side, you see just an illustration of atom. And if we want to mimic this atom with artificial technology, and that is nothing but electrical circuit. So what we want to do is mimic this atomic energy level spectrum with something called as superconducting qubit, which is nothing but electrical circuits. And these electrical circuits consist of capacitor and inductor. This is very basic design. It can get very complicated depending on the usage and what we want to achieve. So let's compare again. This is the energy level diagram, and the x-axis is radius. As we increase the radius, this is the usual pattern we get for energies. And when we talk about this LC oscillator, which we also called quantum harmonic oscillator, it has this kind of potential energy curve, which is uniformly spaced. So you can see these red spacings are uniform as compared to left side, which is non-uniform. But the problem here is we cannot access any 2 given levels, because if the energy spacings are equal, then if we provide certain amount of energy, we cannot control which level is excited to which level. So in artificial atom, what we want to do is to mimic this kind of energy level. And to do that, we introduce non-linear inductor. So instead of just linear inductor, when we replace it with non-linear inductor, the energy level you can see gets split non-uniformly. And now something looks like similar to the left side, where you have bottom two levels more spaced than the upper levels. And to bring this non-linearity, there is a very key element in superconducting qubits, and that is called as Josephson junction. So this is nothing but a sandwich of two superconducting electrodes, and in between we have a very thin layer of oxide which acts as insulator. So if we put this Josephson junction in the circuit, it brings out the nonlinearity, and in circuit terms it is represented by either this box and the cross in between, or this I naught is critical current and this is the junction capacitance. So the Josephson junction can also be represented by this. So this is just one sample image of a qubit in our lab. This is 2D qubit. Of course, this is very single like isolated qubit. In order to perform more computation, we need to couple more qubits with it, but this was the preliminary basic design. So this hole is not just qubit. This coaxial thing kind of, you can see ring, this is qubit, and this spiral thing is resonator. And this again, white thing you can see is coupling to the transmission line. So we'll talk about it. So what are the key elements, circuit elements to construct qubit resonator, or like how to construct superconducting qubits? First is capacitor, then you have inductor, and then non-linear inductor or Josephson junction, and then you have transmission line through which you put your microwave drive in order to know the state of the qubit and also control it. So if in circuit element type, we have resonator, which is nothing but quantum harmonic oscillator, which we just saw with equal spacing. And if we replace it with nonlinear inductor, it becomes qubit. This is a very simplest design. And then we couple it with transmission line. Capacitively, you can do coupling, or you can also do inductively. Both are possible. And this is the very basic circuit for control and readout of superconducting qubit. So you can see this is the qubit, in between is resonator, and then transmission line. So using these elements, we can actually construct many circuit elements and different type of qubit. So different superconducting qubit itself has a whole lot of different type of qubit, but one of the most popular and most common, easy to fabricate qubit is transmon qubit, which I'll focus on and which we also work in our lab here. So just to tell you, get you familiar with transmon qubit is we have Josephson junction, nonlinear inductor, and we connect it to two large capacitances. So these yellow pad, these are metal pads, these are capacitances. This orange thing is nonlinear inductor Josephson junction. We fabricate it on a chip with some substrate, which can be some oxide, aluminum oxide, or anything. And these capacitances, they will have net positive and net negative charges, as shown here by different colors. So by applying gate voltage, we can make them oscillate between these two metal pads through this nonlinear inductor. And that becomes our, very generally speaking, that becomes our charge transmon qubit. So because here we are playing with charges, so if the charge goes from here to here, we have one excess charge here. And if charge goes from here to here, then we have some excess charge here. So typically there are 10 to the power 12 mobile electrons here. And at very low temperature, actually, I'm sure everyone knows here, at superconducting temperature, these electrons, they combine to make Cooper pairs. So they don't behave, or they don't behave like move according to one electron as separate, but they become a Cooper pair and becomes like a pseudo particle. So if one Cooper pair comes from this metal pad to this metal pad, so we will say that this has one excess charge, and that makes the state of the qubit different. So this is just a introduction for charge transmon qubit. So just to see where this superconducting transmon qubits stand with respect to whole spectrum of physics, because in physics we use whole different spectrum of frequencies, temperature, and for different physics. So if we see this wavelength scale, frequency range, and temperature range, so we operate around millikelvin range, around like 8 to 10 millikelvin temperature. This is just the fridge in our lab. This is the dilution refrigerator, which helps us attain this temperature. And we put the sample inside it. And this our circuit is like in the dimension, it is around few centimeter long. So we operate it in microwave regime. So the frequency is like around 5 to 10 gigahertz. And the temperature of this is again few millikelvin to 1 millikelvin, we can operate it. So this is the point where we operate. So as we know that we have electronics which we can control easier as we go down the frequency. So it is a bit difficult to control like components with very high frequencies. So as the frequency decreases, the controllability for us enhances. And also when the temperature drops, then the noise drops, and then we get low noise and better signal. So if we want to isolate a qubit, then it's always preferable to put it into low noise, and that low noise can be attained by low temperature as well. So let's see very few like mathematical thing about electromagnetic oscillator or quantum harmonic oscillator, which we see here. This is the capacitor and inductor, and let's just apply Kirchhoff's voltage law. We can also do it by current law, but just for voltage law, if we see the voltage in this loop should be 0. So the voltage around inductor and capacitance should add up to 0. And the voltage along inductor is just the derivative of the flux passing through it. And for the capacitance, the voltage is charge over capacitance, which should be like 0. And this flux, we can write it as LQL over dt, which is time like derivative of charge, current, and inductance. So just replacing it, we can see the equation, governing equation for this quantum harmonic oscillator. And the Hamiltonian looks something like this. So we know this Hamiltonian consists of kinetic energy and potential energy. And this corresponds, in terms of charge and flux, it corresponds to this equation. So this is for normal quantum harmonic oscillator. But you may see that this quantum harmonic oscillator has a very overlapping similarity between the mechanical oscillator, where we have a simple pendulum hanging, and we like the pendulum is like having a motion, so a rotational motion, and you have two conjugate variables. One is momentum and one is position. So the governing equation in this case is this. And in the case of LC circuit, it is this. So you can see very much similarity. So we can say that the momentum corresponds to the charge, and the position corresponds to the flux. And the canonical Hamiltonian looks exactly same. So this is the similarity of LC circuit. But now, since we talked before, we don't just need a quantum harmonic oscillator, but we need which can be used as two-level system. And that is here, let's see the case of transmon qubit. So we replace linear inductor with nonlinear inductor, and the potential energy plot changes, the shape changes, and you get more like a cosine function, and the spacing changes. So here on the x-axis, you have superconducting phase, you have energy here, and as you sweep this, you get this plot, which is non-linear now. And the spacing, the difference between spacing of 1-2 level and 0-1 level is something we called as unharmonicity, and that is depicted by this alpha. So if alpha is 0, means all the levels have same spacing, so it becomes same to harmonic oscillator. So it cannot be used as qubit. But if we introduce this Josephson junction, it gives us this cosine function in Hamiltonian, and which corresponds to this nonlinearity. So this is what these 0 and 1 we call for qubit, and this is our computational subspace among all the higher space. Sorry, the total slide numbers are not consistent. So we have 2-dimensional as well as 3-dimensional qubit system. So for 2-dimensional system, this is the first qubit realized, like Professor Panigrahi was also mentioning. This was realized in 1999 by Professor Yasunobu Nakamura, which fortunately is also my supervisor. So he showed the first time the coherence in solid state qubits. And then over the years, the design, the quality, and the technique to realize this has been evolving, and it gives to a lot of different architectures by different companies and different labs across the world. Also there, we can have 3-dimensional qubit systems. So these pictures are from our lab. So actually I was working in this qubit system, the left side bottom, until some time, but I have now moved to 2-dimensional qubit system. So 3-dimensional qubit system have their own advantages and disadvantages. Advantages is that it has very good quality factor. So because the mode volume is large, so when you put the signal inside, then it can be trapped very well inside. But what is the disadvantage is that it is not scalable. So if you want to put like 100,000 million qubits, then this itself has some few centimeter dimension, and then it is just impractical to put 1 million qubit, and then you have to put those inside the dilution refrigerator. So that's why we switched to 2-dimensional qubits, which is very scalable. But if you want to do experiments with few handful qubits, then 3-dimensional qubit systems are also very good and helpful. So I gave a very brief gist about superconducting qubit. So until now, we can have idea about why it is more promising than other qubit candidates because of its high controllability, because it is up to us to fabricate of any dimension. And it is also easy to fabricate because the fabrication techniques are just normal electronic industry fabrication, where you like the normal chips gets fabricated for your smartphones and laptops. So the same electron beam lithography technique is used to fabricate these chips. And the controllability is very high. The coupling is very high because it is up to us to make the resonators like longer or shorter, and the qubit size, the capacitance size we can increase. So it gives you total like whole lot of paradigm to play with and give you high controllability. That is why it is very promising. So that brings me to the second subsection, which is control and measurement, and I'll speak on how can we access them. So just to give you a brief operation flow summary, you have your PC and then you want to operate your superconducting qubit, but what is the operation and what are the layers in between? First, you give signals, send signals in the fridge, and this dilution fridge looks something like this. This is one of the fridges in our lab. You see these gold platings. These are different stages of temperature. And this silver cylinders, you can see inside this, we put our qubits. So just here we put our qubits, which is nothing but like I showed a nonlinear inductor coupled with capacitance, and then we can intuitively see it as a block sphere. So this is how we put our signal inside. It comes through this point. So this is where the transmission line is connected. The signal comes through like this. Interacts with the qubit. This is where the qubit is, gets reflected and goes back to your PC where you analyze your data. So now let's see if we want to put microwave drive on cavity. So for cavity, you have your drive, microwave drive in room temperature, you have some wiring, and you have this LC oscillator. This is not yet qubit, it is just a resonator with quantum harmonic oscillator on chip. And this is what we get classical Hamiltonian. So we just saw this was our Hamiltonian, and this is just the drive Hamiltonian. So in a canonical system, we have the system drive, and this is extra drive term because this is what we want to use for control and readout. And now instead of cavity, we connect qubit to the microwave drive. So this is on-chip superconducting qubit. You want to read out and control through your room temperature. So what you do is you connect your superconducting qubit to transmission line via some capacitance. So this is just capacitive coupling. So you put your input signal, it gets reflected back, output signal, you have information here, you analyze that. And then because it is quantum harmonic oscillator, so your quantum operator, they changes to ladder operator to raising and lowering operator, because here we just talk about two-level system. And your Hamiltonian for qubit becomes something like this. But is it a good way to talk to a qubit? So if you connect a transmission line to qubit, but it's not a very good way to talk to qubit. Why I say that is because first of all, you want your qubit to be isolated and not get disturbed by any noise. But at the same time, you also want to talk to it. You want to see what is going inside and you want to control it. So you have to give some opening to it. If it is perfectly isolated, then it is of no use. But then you have to do something with it. And that brings us to coupling it with anything outside which you can control. But if we directly control it, if we send our signal through it, but with signal also goes noise and it gets disturbed the state of the qubit. So if we just put signal brings noise, and that can lead to uncontrolled random bit and phase flip errors. It leads to noise and dissipation. And intrinsic, there can be intrinsic losses as well. And also input-output channel also leads to two different kind of relaxation times, which we can see here. So in our block sphere, you have transverse axis, which is XY plane, and you have longitudinal axis. And if you have transverse noise, then you have your qubit state flip relax from 1 to 0 and 0 to 1. So this is what we call as T1 error relaxation time. And if you have longitudinal noise, then if your state is on the XY plane, then you have pure dephasing. Then your state dephases on the XY plane. And of course, noise is not like just one particular kind of noise. When there is noisy environment, then you have all types of noise. So these both noise, they occur on your qubit, and we call it as decoherence. So that is why this noise is very important. This coherence times are very important to characterize our qubit. So the longer coherence time, the longer time you can do your quantum operations. So we can see this the coherence times as like the lifetime of qubit. So until the qubit decohere or like relaxes, you can do as many qubit control and readout as possible. So the shorter you have relaxation time, you can just do less number of gate. So that is why this is a very important metric to characterize any given qubit. So that brings me to a summary of the coherence times of superconducting qubit over the years. So like I said, in 1999, it was the birth of the Cooper pair box, which was the first superconducting qubit. That time, the qubit lifetime was few nanoseconds. And over 2 decades, there has been very impressive and considerable amount of improvement. You can see here. Now, some Josephson junction-based qubits even have touched some millisecond qubit lifetime. So this has been possible because of exhaustive research all over the world and changes in the design, in the electronic part, in the fabrication part, and also in the software and hardware parts. So this has been just the upward going trend in terms of superconducting qubit. And this proves how coherence times are crucial for quantum computation in superconducting qubit, and also why it is promising, because there is no saturation yet, and it is bound to just increase further. So like I said, it's not an ideal way to talk to a qubit. So then what do? We don't want to just disturb the state, because then the quantum information is lost. So what do we do here is we put a resonator in between. So like I said before, this curly thing, spiral thing is meander, is readout, which is quantum harmonic oscillator, which circuit element representation is this. So what do? We don't talk directly to qubit, but we put resonator in between so that it doesn't disturb the quantum state here directly. And also when quantum state like emits, it doesn't directly emits to transmission line. So we can have a very good analogy with cavity quantum electrodynamics. I'm sure a lot of audience here are familiar and like expert of cavity quantum electrodynamics. It is in the optics. So here the qubit is atom. You put inside a cavity and then you put some drive to interact with this atom inside. So if we take the analogy, the atom is corresponding to this superconducting qubit here placed, and this cavity is our LC circuit. So you get this mode, microwave mode, and then this generates this electric field, and this electric field couples with the qubit inside, and that's how you get interaction between it. So this serves as the cavity for superconducting qubits. The good points here, cavity electrodynamics, is it has very long coherence time, because once the signal comes, it reflects a lot of times here inside and interacts with the atom before leaving outside. And the coupling is with optical light, because optical light is it is used for communication purposes also. So ultimately, we want to have this optics to send quantum information from one point to another point. So if you have coupling directly with optical light, then it is very good. But at the same time here, you have design flexibility. You can design any kind of circuit here in circuit QED. There is no trap required as compared with external cavity, and the coupling regime is very strong. So like I said, if you change the dimension of these resonator, you can make the coupling stronger or weaker. But are quantum measurements so straightforward? So let's just take very basic example, which I found very interesting and funny also at the same time. Let's see that if you have a barrel of oil and you want to know, are there any fumes coming out of the barrel? So like without opening, you cannot say. So one very direct way is to do something crazy and light a matchstick and put there. So you will get the result, but with very dire consequences. If there are no fumes, you are safe. Otherwise, you get the result, but with a very heavy price. But at the same time, there is another option, if there are fumes coming or not. If there are fumes, and let's say there is some technique, you'll shine a laser, there is kind of some reflection or some reaction, and then you record it. Then not only you get the state of your question, like answer of your question, but also you preserve your system as well. So very aptly, the name is given as demolition and non-demolition quantum experiments. So both types of measurements could be done in circuit QED. So the first demolition is direct monitoring. Like I said, if you put signal, the noise comes, you get the state, but it is all demolished. But again, if you put a resonator in between, then you can get the state of the qubit, but it is also preserved. So it is non-demolition, and thus there is no spontaneous emission, because your qubit is not directly coupled to the transmission line. So this is what in circuit QED is called dispersive readout. So this is just the idea of dispersive readout. You have this cavity frequency in the circuit. It depends on the qubit state. So the first, this 0, 1, 2, 3 are the average photon number in your cavity, and G, E, F, these are the state of your qubit. So depending on how many photons are there and what is the state of your qubit, this omega R is the resonance frequency of cavity. So this omega R, G and E are different. So depending on if your qubit is in G or E, your resonance frequency of your resonator changes. And that is what we want to utilize. And that is what is the principle of a readout. So the cavity frequency depends on qubit state. So we send a signal, it reflects back, and we get this spectrum. So if it is in 0 state, your frequency is this blue line. And if it is in 1 state, this frequency is in red line. So without disturbing the qubit state itself, we can know the qubit state by measuring the frequency of the cavity. Which brings us to the final part is how to control it. Now we have seen how to read out the qubit state, but we just don't want to read out. We want to do some operation, so we want to control it. And in control, we have 3 basic control: X, Y, Z control, which can make up to any kind of rotation. So for X and Y control, we can directly put a microwave drive, which interacts with the qubit state here inside. And you can change the phase of the microwave drive. So if your phase is 0, it corresponds to rotation along x-axis. And if your phase is pi/2, it corresponds to rotation along y-axis. So that's how you can make your X and Y rotations. How about Z control? So you can make Z control very effectively in superconducting qubits, especially in transmons, because in transmon, you don't have external flux bias to change the frequency. You just have fixed frequency transmons. So what do you do is, instead of 0 and pi/2, you can do some particular phase for your microwave drive. And what does it do is just change the frame of reference for your qubit. And that effectively makes the Z rotation. So basically for Z rotation, you don't have to put any external drive. It is just, if your next signal is X signal, then instead of some phi phase difference, you put phi plus sigma. So that sigma would be your rotation along Z basis. And in the case of your tunable qubit, what you do is you just change the frequency of your qubit a little bit, because if you change the frequency of your qubit, then this block sphere rotates and it gets new frame of reference, and that is your Z rotation. So Z gate is just a deviation from your assumed frame, which is very simple to implement. And now we will see 2 superconducting qubits coupled, and this is the level diagram. You have this 0, 1, 2, 3 photon, average photon in your cavity, and then you have the state of 2 qubits, GG, EG, GE, and so on. So for 2 qubit, you want to focus your operation in this qubit subspace, which has these 4 energy levels. So there are numerous ways you can implement 2 qubit gates in superconducting qubit, but the main are like static, where you have your energy interaction, and the second is parametric drive. I will tell briefly about it. So using exchange interaction is this static coupling. So don't get very tensed about so many lines and these diagrams. It is nothing but if we want to do C phase, and what we do here basically is change the frequency of one qubit and bring it closer to the another qubit. So we keep one qubit as it is and we change the frequency. So let's see this 1-1 state of one qubit, this black dot, we change the magnetic flux, and with magnetic flux changes the frequency. We bring close to this point and then again go back. And this point, like the amount of time required, it will accumulate the phase. So that is how we can have some phase gate, control phase gate. And in terms of ISWAP, we need to do actual qubit information exchange. So we do it by 1001. We bring it here, and this is more closely, you can see this point. We bring more closely here, there is actual energy exchange between it, and then we get ISWAP gate. So this is changing the frequency of your qubits and making gates. So ISWAP is non-adiabatic because it changes actually the state and changes the population between these two. It is very fast gate, but in terms of control phase gate, we have to move it very slowly so that there is no population enhancement in 2-0 state. So I know that it is like not very exhaustive explanation, but like there are so many gates and so many methods. This is just to give you an idea of how what are the two approaches. One approach is you change the frequency of either of the qubits or both qubit and do some gate, but without changing also you can do, and that is what we do in our lab, is parametric coupling. So you can opt for architecture where you cannot change your frequencies. So that is what we also use in our lab. So the disadvantage is you cannot tune the frequency of qubit, but the advantage is that the noise is less, because if you want to change the frequency of your qubit, you have to put extra flux line for each qubit, and that complicates your wiring and your crosstalk, and it just is not very positive or favorable thing to do for scalable quantum computer if you want to make thousands and 100,000s of qubits. So another approach to do two-qubit gate is cross-resonance gate. So until now we have seen that depending on the state of the cavity, your E and G qubit state can also be changed. But how about just talking to qubit? So depending on the qubit, your another qubit changes. So in cross resonance, what we do is we drive one qubit on the GE transition frequency of another qubit. So we don't care about the state or the photon occupation probability in cavity. We just drive one qubit in the frequency of second qubit, and this is what we get. So this is like the control. Control is the qubit. Like in C0 gate, we know the qubit which determines what happens to the other qubit, and this plot is for the target qubit. So you can see this blue is for control is in 0. So if one qubit is in 0 and the target qubit oscillates in this direction, but if the control is in 1, it oscillates on the second on the opposite direction. So this is what is cross resonance gate, and cross resonance gate is 2-qubit entangling gate. And from this cross resonance gate, we can construct C0 gate by just combining a couple of single qubit gate also. And as we know that by using arbitrary single qubit and C0 gate, we can construct any logical circuit. And that is why I spoke about these cross resonance 2-qubit gate and single qubit gate, because by using these, we can practically construct any quantum circuit. And now just, I know it's already 7 minutes more, so I will just tell about what people have been doing, achieving using the superconducting qubit. You must be knowing about a very hot topic right now, which is variational quantum eigensolver, and where we combine quantum computation and some classical computation to find the ground state energies of a given molecule or some optimizer. And here these thick lines are single qubit gates, these dashed lines are 2-qubit gates, and these thin lines are measurement. So if we have these 2 qubits, we do some operation, we get the expectation value for a given Hamiltonian, we do classical optimization and get a minimum value, and correspondingly we will get some new parameters theta, and then we optimize it and then feed again it, and it goes like iteratively until we reaches the minima depending on the given precision. So this is a hybrid algorithm which consists of quantum and classical both approaches, and this is just hydrogen ground state energy. So this is whole different field of research right now, variational quantum eigensolver, and a lot of things have already been demonstrated. And another one again was from IBM, where they used hardware efficient VQE, and the need for hardware efficient is to make the circuit more compact, because of the reason is that, like I said, the coherence times are still limited in superconducting qubits as compared to, let's say, spins. So we cannot just make quantum circuit longer depending on our will and wish. So we need to make it compact. So that for further like to know further about this, you can refer to this paper or contact me later. And yeah, thanks for your attention. It's been great to discuss here. And this is my lab, Nakamura Osami lab in the University of Tokyo. Now you can ask your questions, and if there is less time, you can always drop email to me and we can discuss further about this. Thank you.
Thank you, Akil, for a wonderful talk. Very, very nice talk. Now, questions, please. You can unmute and directly ask. What is the kind of thing you people are looking at? Now that this is a question from my side.
Yeah.
What is the kind of research or what is the kind of problem you are looking at?
For us, the main project is about making a scalable quantum computer. So we have already made 16-qubit chip, and we have fabricated 64-qubit chip. So right now, our main theme is to make scalable quantum computer and show like quantum error detection and some algorithm for higher number of qubits.
And how about at the level of basic science, for example?
Sorry?
Level of basic science, like for example, any scientific question?
Yes. So for that, we have different verticals. So there are actually three things going on. One is this integration project, which is more of an engineering thing. Of course, there are some scientific things. Another thing is this hybrid thing. We have also a team here which works in magnons. So we have like coupling of superconducting qubits with magnons. And another thing is hybrid team with respect to optics, because we want to make a whole system where we have quantum information, some computation in microwave regime. Then we couple it to optics, which can transmit it to a larger distance. So we also have a team which are working in coupling this microwave to optics side. So that is more of a scientific approach, because we need to have good coupling and how to come up with the system to couple it.
Any questions from the chat box? Avinash, can you see anything?
Yeah. So there is one question: how superconductivity arises in high temperature superconductors?
High temperature superconductor, I think since it's not like the domain of my research, but I think superconductivity phenomena is same. It's just that since the superconductivity, what we realize now, it comes in the very low temperature, but like there is a very considerable research going on to realize high temperature superconductor, so that we don't need these dilution refrigerator and everything, because if you can achieve superconductivity at room temperature, then of course we can just do get away with these dilution refrigerator. So I think the phenomena of superconductivity is same. It's just like the research is on what material to come up with, and how you can get something which has the critical temperature is a bit higher. So that is the ultimate, I think, goal of this field, if we can realize it in normal room temperature. But as far as research about just high temperature superconductors are concerned, like it's not happening in our lab, and it's not like domain of our research right now.
I have one question.
Yes.
So you said that we don't usually have a two-level system. In general, we have multiple levels, and we model a qubit out of it. So yeah. How do we do that precisely?
Yeah, it's excellent question. So actually, that is what brings us to this electrical circuit controllability in superconducting qubit. So me show. Yeah, so here, if we want to tune these differences, so actually in fabrication, we can decide the junction, capacitance, junction area. So this overlap, you can see this overlap of one conductor onto another. This is the junction area. So if we reduce this area, then we can have different value of capacitance, inductance, and that brings us to this controllability here. Yeah, so here then we can change this this separation. So this enharmonicity is changed mainly by the design of the Josephson junction. So everything remains same. If we change just the design of this nonlinear inductor, then this alpha gets changed. So if we can make alpha like larger or smaller, we can tune the difference between these two.
Okay. So can we make, since we have multiple levels, so can we model a Qubit out of it? I mean, 3-level system.
Yeah, we can model, and there have been some experiments using Qubit as well. But the problem arises is that the coherence times are almost like half of what we get in GE. So there are some like algorithms which need Qubit, and even if they don't need, but in some algorithm we can use these the third level as some ancilla qubit or ancilla level. So there have been some work, but since the loss are high, so we cannot store like information in higher levels for a very long time. So it's not as useful for normal like computations, but for specific problems, it is very useful and people have used it. So yes, we can use this Qubit. And also this Qubit is used in qubit reset, because if you need to do computation many times, and if after applying a gate, you again need to initialize the qubit, which is one of the requirements for quantum computation. So you need to like remove the population from your excited state to ground state in a rapid manner. So what we there is one technique is what people do is excite whole your population to the second this 2 level, and then that level has higher loss. So the rate of loss is high, so your qubit relaxes much faster than GE state. So the second excited state is useful in different ways.
Yeah, excellent. Thank you very much. And it was a very nice talk, guys.
Thank you.
Yeah, I really enjoyed it. Very, very nice talk. Thank you so much, Akhil. Okay, so let's say thank you to Akhil, and hopefully when you come to India, pass to IISER Kolkata, we would love to host you and hear from you. Thank you.
Thanks for your invitation. It was lovely talking.
Thanks.
Thank you.